What's up everybody, this is Cakez, and in today's tutorial you will learn how to fully initialize and load OpenGL until you can see a triangle on the screen. Now this tutorial is going to take a while because I will go into depth on how OpenGL is loaded behind your back, aka what Glad or any other libraries do for you, so that you have the information required in order to understand how that is done, which obviously comes at the cost of a lengthy tutorial. So let's get right into it. So first we need to get rid of these log messages right here, and we should begin by opening or creating a new file called glrenderer.h. This is going to be our rendering interface, and we put that into source. Start with a pragma once. Then in order to actually get OpenGL stuff, we need to download some files. You can go to the registry of Kronos, and then over there I'll put the link in the description. We want to download a certain file here, or a couple of files. We need the core OpenGL profile. Then we need the extension profile, because we want to use OpenGL 1.2 and above. And then for Windows, we want to use the Windows GL extension. GLX extension, this is for Linux. We'll use that later, but not in this tutorial. So I guess we'll download all of these files now. And then we put them into a new folder on Celeste clone, which is called third party. And then another one that we need is the KHR platform.h, which seems to be like a shared platform header from Kronos. And so this needs to be in a folder called KHR. So we create a new folder here, KHR, and then we put the file in here. And so you should have these files in here. And then what we need to include is the GL core, which is important because it has a lot of function definitions that we need now. So let's start by pasting in what we have to do, or how OpenGL actually is being loaded by Windows or any other platform, because there is no tutorial out there that I could find that actually explains how this works. And so in OpenGL, what you have to declare is static function pointers. So let's say we have a function pointer to, for example, the commonly known GL create program function. And this stands for a pointer to a function called GL create program, and that is a proc address. And proc address means this is a pointer to a function that we have to load from a library, and then we call that GL create program underscore pointer. So basically saying that this is a function pointer to a function somewhere. We don't know where that is yet. This global GL load function is going to load all of the OpenGL functions that we will be using in our project. And this is where we have to differentiate between Windows and Linux already. On Windows, you have a function that is called Windows GL get proc address, and that takes in a pointer to a string, and that is usually the name of the function, which would be GL create. And I just noticed I had a spelling mistake here. That is GL create program, and that is the function, and that gives us back a proc address. You see that proc right here, and I guess I call it proc as well. And then we can check if we actually got back something. So let's say we have the proc address, then we are good. The only thing we have to check is if we don't have the proc address. Unfortunately, right at the top here you see WinGDI. This is an accidental include. Please don't pay any attention to it. It is wrong and shouldn't be here. I just didn't manage to cut it out. And now once we have that proc address over here, we could say, okay, well, the GL create function pointer is that proc address. And then we need to cast that obviously to a PFN function pointer of create program. And then what Glad and the other libraries are doing, you don't want to call this function pointer. They don't want to expose that function pointer to you. You want to use the commonly known function pointers or the function names. They define the headers for you. And so the way this looks is you do a GL API, and in this case it is a GLUint API entry GL create program, and it takes in a void. And then this function calls our GL create function pointer, and in this case it returns the result of that because we actually have a return value. And this is how Glad, for example, works. Glad defines you this pointer. You don't see that pointer. Then Glad will check whether it can load the function pointer, and this is loading from the Windows library. It is called OpenGL32.dll. And then if it can find the address of the function, if it can find the function, then it assigns it to the pointer, and then it gives you a wrapper around that pointer that is then called like the normal OpenGL function that you're used to using. And I want to do some cleanup before we continue, because this is obviously Windows stuff, and if we want to have something running on Linux, then we can't have Windows stuff right here. And so this is where we need to go into our main file, and right here you can see that there's Windows globals and the Windows platform. All of this stuff should be extracted out into its own file. So essentially what I want to do is include a win32 platform.c++ file here if we are running on Windows. So then we extract this, so we don't need that anymore, the section, and then everything that comes below here will be inside the Windows 32 platform.cpp file up until the end if. We copy that out and then we create a new file under source, call it win32 underscore platform.cpp. And then in here we paste all of this. Then over here we have the platform specific stuff, which in my opinion should not be inside of the main file. So we create another file which is called platform.h, and then we go back and extract the globals and the functions out of the main and put that in platform.h. And now the way this is gonna work is that we have the platform.h file, which should be platform agnostic. It gives us functions that every single platform layer has to implement, and for example Windows is the first one that implements the create window and the update window function, and we will have to implement the same functions on Linux as well. To finalize this setup, make sure that you include the platform.h file and the schnitzellib.h file in the win32 platform.cpp file. We'll then switch over to the main file and include the platform.h file in there as well. And finally switch over to the platform.h file and then add a pragma once at the top. Since we are including it in two files now, we need to make sure that it is only included once. And this will be called platform underscore load underscore gl underscore function. That takes in a character pointer to a function name. And this needs to be implemented by the platform. So now we can go back into the GL renderer. Let's copy this code right here. And then we go into the Windows platform and we paste it here. Then we implement the platform load GL function by returning the proc address at the very bottom. Unfortunately, this is not enough to safely ensure that we are able to load all of the OpenGL functions. To be honest, I don't know exactly why that is. It might have been a mistake on my part. I don't want to count that out. But essentially, we have to make sure that if we can't load the function, we need to load the function in a different way. And we do that by loading the OpenGL32.dll directly from the Windows system. If you have a graphics card that supports OpenGL, which everyone should have, you will have an OpenGL32.dll file on your system, which is the library that we are loading right here. Static means that this line of code is only happening once. And so in case we don't find the function, then we load in this OpenGL DLL and then we try to get the proc address from this file. And for that, we need to call the Windows function get proc address. And then over here, we also want to try to get the function name, not create program. Okay, and if by this point we didn't find the proc address, then we actually have to throw an assertion. And I would also like to return null pointer, just to indicate that we actually did not find any function at all. After that is done, we switch back to our glrenderer.h file, in which we call the platform load GL function with the function parameter GL create program. And the way I get access to the platform function in the GL renderer is because I'm including it below the platform layer. Testing if you can build right now will result in the following error. The header file glcore cannot be found. And the reason for that is because the compiler doesn't know where to find or look for it. Next to source, we have the folder third party that we created, and this is where it is located. The compiler needs to know where to look for this file. We have to include those in the build as well. So we need to have another variable here which is called includes. And then we type in -i third party and -i third party /includes, which means that we are including the directories to be searched for C++ or header files. And obviously the includes have to be put inside the clang command as well. But it gives us a linking error now. And that means we also need to link with this. Okay, so it's successfully built. So we are now linking with OpenGL. Okay, and that means we are now successfully loading our first OpenGL function. And since I don't want to sit here and show you all of the functions, what I will be doing is I will basically copy and paste all of the functions that I'm loading in the current engine into here. And then I will give you the code through pastebin so you can copy and paste that file as well. Because there's no need for me to type that out. It's boring. Alright, let's do a quick overview of what we are doing here. We're getting all of the functions that we need for OpenGL. We're defining them as function pointers up above. Then we have our function void loadgl functions. And this is where we call down to the platform loadgl function. And then down below we are defining all of the headers or the wrappers for the functions. So we can call them normally in the engine. And this is everything the header file for OpenGL needs to be doing. And the reason why we are including glcore, for example, is because it gives us all of these defines. Otherwise, we would have to define these things ourselves. So no, we obviously need to initialize OpenGL, and for that we need to do that together with the Windows window. And in order to do that, we have to include the core into our main file as well, because We will need access to this on the Linux window and on the Windows window, and maybe if we ever make a Mac window, on the Mac window too. After including GL core into our main file, we notice that in the Win32 C++ file, there is a warning popping up telling us that Win32 lean and mean is already defined. And that means that Windows is already being included. If you take a look into the file, then you can see that it is trying to look for app entry. If it is not there, then it will check if Windows lean and mean is not defined. If so, it will do so. And it will also include Windows NH. And so we definitely want to avoid that because we want to include Windows ourselves. GL core seems to already define Win32 lean and mean, which we defined before, which means that GL core is including some Windows stuff, and we don't want that. We can just define the app entry, and then GL core doesn't include that. And then in the platform, we should no longer have this yellow line here under lean and mean. Now we're going to actually initialize OpenGL on Windows. And in order to do that, I want to quickly give an overview of how that is done. First, we have to create a fake window, and from that fake window we get a device context. This is a Windows handle, and then from that device context we get a rendering context for OpenGL. And then if we have that, then we can load functions that will help us set attributes for the next window that we create, which is something like what is the depth of pixels, or how many bits are for pixels, what options do we set on the window, and stuff like that. In order to get those functions, unfortunately, we have to do some weird stuff where we create a fake window and then get those functions and then delete the window and the rendering context and then start all over again, which unfortunately, in my opinion, is very complicated. But I'm going to show it to you anyways, just so you know how it is usually done behind the scenes, like for example when you use SDL2 or GLFW or something similar, right? And the way I would like to do that is by creating a local scope here, because in order to initialize OpenGL we need to create a fake window, and this is where we begin. We need to create a fake DC. That's a fake device context. I call it fake DC. This is a Windows function actually, get DC device context, and that takes in our window that we defined above here as a static. And then I do that, you don't have to, but if we don't have a fake DC, then I do an SMS search. I'm gonna try it, continuing with a higher zoom. If that is zoomed in too much, please respond in the comments and tell me if that is too close or not. And so now we need to create a pixel format descriptor. This is where we have to set in some stuff, like for example the size. Then you set the version. And then this is the first one that is actually interesting, the flags. Draw to the window. We want to support OpenGL, and we want to do double buffering. I'm pretty sure you have heard that before, but if you don't, it means that we get one image from the GPU. It gives us like one thing to draw on, then we draw on our image and we give it back. And then the GPU will have like a second image for us. We don't have to wait for this one image to be done. We can take the second image and then draw on that already, and it's keeps interleaving the two images. Then we set the pixel type, which is the pixel type RGBA. The rest of the options are the size and bits for color, alpha and depth. And after that, we choose the pixel format by supplying our fake device context, as well as a pointer to the pixel format descriptor. And then again, if you want, you can do the error checking. The next function is a little bit blurry for me. So basically what we're doing is we are setting the pixel format that we have just chosen on the device context. And for reference, I have the documentation right here, which is basically not very helpful. But if you scroll down a little bit further, you can go to the remarks section. And this is where it references the rendering context. Basically what this is saying is that the set pixel format function also changes the pixel format of the window. And then it goes further to say that setting the pixel format of the window more than once can lead to significant complications for the window manager and for multi-threaded applications, so it is not allowed. And this is the reason why we have to create two windows. Obviously, if we are not able to set the pixel format, we can toss an error. And then finally, we create the fake rendering context. This is done by invoking WindowsGL create context using the fake device context. And then using that rendering context, we can call WindowsGL make current, which means that all subsequent OpenGL calls made by this thread are drawn on the device identified by the rendering context. This is where we can finally load in the functions that we need to set on our window. So the first function is we need to set our pixel format and we need to set attributes. Basically that says what OpenGL version we use and what format of pixels is our window using. And this is when we don't get any IntelliSense, and this is where the WindowsGL extension comes in. This is where we have to include that. At the top, include WindowsGL extension.h. we need access to two functions. First, the Windows.gl choose pixel format function, and then the Windows.gl create context attributes function. We get the function pointers by calling our platform low.gl function and then supplying the function name as a string to the function. And then below you can check if you have gotten a proc address back from both of these calls, and if you don't, then you can return false and do an assertion, of course. Okay, so now that we have these functions, let's hope we have them, right? Let's say we have them and everything works fine. Then we need to basically destroy everything we just created and recreate that again, because we can't use this rendering context, because we have to set attributes on the window before we actually create a rendering context for OpenGL. And in order to do that, we need those two functions. So basically, we need those two functions to set stuff on the window, but in order to do that, we need to create a window first, delete it, and then create the window using those functions. That's usually what Glad does for you behind your back. The cleanup is quite simple. We just call Windows.gl make current with 0. Then we call Windows.gl delete context on our fake rendering context. And then we call release device context on our window using our fake device context. And after that, we also destroy the window. Unfortunately, but I've explained that before on why we do that. And then after that, we redo the same thing. So to begin, we create a new local scope and call that the actual OpenGL Initialization. Only this time I want to add in a little twist. The one thing that we didn't do last time. I want to add in the border size. And why do we do that? Because in Windows, when you create a window of a certain size, it doesn't take into account that, for example, the heading of the window has a size and there's like these tiny lines on the left and right and on the bottom of the window. And we have to take these lines into account if we want to create a canvas of a certain size. We are interested in the canvas, the client area of the window, and not the stuff outside. We can call a function called adjust window rect ex. That's the extended version that takes in a pointer to the border rect. Then our style from the window, which is the DW style. Then if we want to use a menu, which is no, and then the extended style. And since we don't supply an extended style when creating the window, we're just going to supply 0 here as well. And then it gives us a rectangle, and we want to increase our width and height by that rectangle. And so in order to speed this up a little bit, I've copied the create window function, the assertion below the window function, and then also the part where we got the device context from the window. And then I start creating the const in pixel attributes array, and at this point I realized that it is easier if I copy paste in certain things beforehand, before actually explaining them, because oftentimes they don't make sense without seeing the full picture. I think it's easier to go over it like this instead of me typing it out. Basically what this means is we would like to draw to the window, we would like to support OpenGL, we would like to double buffer, we would like to set the swap method to copy. The pixel type is RGBA, and then we have the pixel format, again like how many bits we set for each pixel. And then there's another thing we have to do. We actually have to terminate this array using a 0. Not sure why that is, but that's what OpenGL expects, otherwise it throws an error. And I'm going to paste in the next function, because otherwise you don't understand very much. Okay, now this is where we actually call our function Windows.gl choose pixel format architecture review board. And as you can see, it takes in almost the same attributes as before, but it's slightly different. We are now calling the actual OpenGL function that we are interested in, and we are storing that format in our pixel format in however many formats we have. And so I just noticed that this is red, and the reason for that is because we created a local scope above. If we go up here, we created these locally, which is fine, but we should do the following. We should extract these out to at least up above where we have the local scope right here, and then we just define them here. And what I like to do as well is call them null pointers, so that it's easier for us to have an initial value. You don't have to do that, you can just define them. And then obviously down below we assign them without the definition. So it should look something like this. And this is the first function that we need to call. And if we are not able to call this, then we need to return false, because we weren't able to choose the pixel format. Okay, next. And I think it's easier this way. Tell me if you want me to type it out, or if you like it more when I paste this in. Especially for these things where it's easier to explain them once they are on. We need to define again another pixel format descriptor. And then this time we describe the pixel format using our device context. Which means that we have already set the attributes here, and we can now get the pixel format out of our device. And then we set the pixel format again like before. This is the same thing, but the only difference you can see here is that we set the attributes and we call the Windows.gl choose pixel format function. The last thing that I copied in, we are almost done. We need to define certain things about our OpenGL version before we actually create our rendering context. And over here we are setting the major version to 4 and the minor version to 3, which is OpenGL 4.3. And then we set some other flags, for example, which is the profile mask. It's the core profile, so no extended profile. And then we set context flags, which are debug flags. This will allow us to have debug callbacks when something is wrong. For example, a shader failed to compile. Then it gives us the option to set a callback in OpenGL, and we'll set that up later. That gives us an error message out to the console and then we can read, okay, actually the shader failed to compile because a variable name was wrong or something like that. And then again we terminate the error. This is where we call our last function that we had to load in, which is the create context attributes. And that allows us to get a rendering context, which we will then make the primary rendering context on our device context. And if all of that works, we have successfully initialized OpenGL on Windows. And that is everything that OpenGL or GLAD, GLFW or SDL, this is what they do for you. Usually extracted out into one function. I'm pretty sure we're going to get like 1 or 2 errors when we build, but let's test. Okay, we are missing a link. This is actually what I was expecting, because we didn't include or we didn't link with another library of Windows. We only linked with OpenGL 32. We need to link with GDI 32. So apparently we are able to initialize OpenGL on Windows already. And I think this is a good place to do a commit and push. A lot of coding, nothing visual, but we are able to now actually use OpenGL on Windows. On Linux we will have to do the same thing, but we already have all of the boilerplate out of the way, so that should be much easier. What's up everybody, and welcome back to yet another tutorial. And this time we're going to fully create the OpenGL renderer until we can see a nice little triangle on the screen. And this time we're going to create a new file called glrenderer.cpp. And the first thing that we're going to include in the file is the glrenderer.h to get access to the OpenGL functions. Now I'm going to create a section here, OpenGL structs, and I know that we will need to have some sort of global context for OpenGL to hold data, like for example access to program IDs and access to texture IDs. And so I want to create a struct called GL context. This one will hold a GL uint program ID. Then below this section, I want to create a new section that is called OpenGL globals. And for now, we're just going to create a static GL context and GL context. This is going to hold all of our global state. And the reason why I'm making this global is simply for me to make it easier to deal with this. The OpenGL renderer will only have access to this in addition to the main.cpp file. For example, right here, instead of including the glrenderer.h file here, we are going to include the cpp file now. And then below this, we're going to put in the OpenGL functions. And then below the section, we create a void, or let's say bool GL init. And this is a good place to give a short but simple explanation of how OpenGL works. When we are using OpenGL, a program runs on the GPU. This program takes in data from the CPU and then transforms that data in a way to display an image to the screen. And the way that works is we have what is called an input assembler, which basically takes in the data from the CPU, which are the vertices. And without going into too much detail, this input assembler supplies these vertices to the vertex shader. That is a program, just like a C or C++ program, that has a main function and that is then being invoked for each of these vertices. For example, the job of the vertex shader is to transform these vertices into the correct coordinate space. We then have optional steps like tessellation and the geometry shader, which can help with detail generation. For example, look at this. We have this human head right here, and it gets more detailed as we go up with the tessellation. In our engine, we're going to skip these 2 steps and go straight to the rasterization and the fragment shader. You can think of the rasterization and the fragment shader as a pixel grid. Think of an image that has a certain amount of pixels in width and height. Taking in these vertices, we are calculating which of these fragments are hit and therefore need to be colored. The reason why this is called fragments and not pixels is because the final image is a result of a bunch of fragments layered on top of each other. Meaning if you draw a ball to the left right here first and then the triangle after that ball, the triangle will cover parts of the ball, but the ball will still have filled in some of the fragments that are also being covered by the triangle. The final result is then an image which is being presented to the screen. Now obviously this is a very simple abstraction, but it should give you a general overview of how it works. And just to reiterate, the vertex shader and the fragment shader are both programs that run. The vertex shader will run for every vertex, and then the fragment shader runs for every fragment, which means the more computations you do in your fragment shader, the more it will impact your performance, because you have way more fragments than vertices. Just keep that in mind, don't worry about it too much, and let's continue. Now, and I know that we will need access to something that we don't yet have. An OpenGL program needs a vertex shader and a fragment shader, and most people just put in the code for these shaders right there into the program, but then later on they go ahead and change them into actual files. But I want to give ourselves the capability of loading and reading and saving files before we actually write the OpenGL renderer. In order to do that, we need to be able to allocate memory in order to save and load the files. And this is where a structure, a bump allocator, comes into play. And I call this a transient storage. This transient storage is a block of memory that we will allocate when we start the program, and then every frame, basically every run through the update loop, we will reset the memory here so that other modules in the game can reuse the memory. And now I want to go into the main file. Since we are already including the GL renderer in the main file, we also obviously have to call GL init, and I suppose I didn't save the GL renderer file because we just started the function. Make sure that the GL init function looks like this. We return true here, and then in the main file there should be GL init should be available now, and it takes in a transient storage. Now we don't have this right now, but I'm going to create them right here on the stack. Bump allocator transient storage, which is make bump allocator, and then the size of that, let's say, is 50 megabytes. And now we don't have this megabytes define, and so we have to go into the schnitzel lib at the very top, and this is where I want to add in one or more defines. We already have the debug break here, which I guess we keep at the top, and so I'm going to paste in something real quick here. The first one is a simple bit macro that we will need later. It basically, you call this macro and then it shifts number 1 to the left by however many places you put into the bit. Unrelated to this, we have kilobytes, which is basically a macro that allows us to define however many kilobytes we would like to allocate if we were to, let's say, allocate memory, for example. And this is also where we use the megabyte macro right here. It basically takes the kilobyte and then multiplies that by 1024. And the same thing holds true for gigabytes. It allows us to allocate a transient storage with 50 megabytes of space. And the reason why I'm using 50 megabytes here is because later on when we allocate sounds, we are going to need the 50 megabytes because a sound of about 2 to 3 minutes or 4 minutes is close, if it's a WAV file, that is close to 50 megabytes in space. And that's why this is so much. Okay, and then we supply the transient storage as a pointer to GL init, which means we can now use this transient storage inside of OpenGL. The first thing we call is load GL functions. We need to make sure that the pointers are all set, because we still have to call this function. Okay, and the first thing that I want to set up always when initializing OpenGL is a GL debug message callback. And this one is one of the functions that we load in through the pointer, in case you're wondering. And so the first thing we have to put in here is a callback, like one of our own functions that we decide that is being called whenever there's an error in OpenGL, or whenever there's some information. And I always call that GL debug callback. And then for the user parameter, I supply a null pointer. All right, let's create this callback. And since this one is a little bit more complicated, I'm just going to paste it in. So we are creating a static void app entry GL debug callback that takes in an enum type of source, an enum type, an enum ID, a severity and a length of a message, an actual message, and then a void user parameter. And so what we are doing here is we are checking on the severity, whether it is low, medium or high, and then we are asserting, instead of 0, we should use false here. And then we are printing out the OpenGL error message with the message they supply to us. Any other message is just being traced to the console, just for information purposes. We don't need this, but I like putting it here, so we get all of the information that we need. And yeah, this is how you set up a debug callback in OpenGL. And there's one or two more things that we have to do. We have to also enable a GL debug output synchronous. And then we also want to GL enable the GL debug output. So you might have noticed that this GL enable is red and it doesn't know, or the program doesn't know that it exists, but it does. And the reason why is because before we include GL core, we have to define something so that it includes actually all of the function definitions that we need. Over here we define what is called a GL extension prototypes. This definition will include more function definitions that we need. So yeah, okay, after we are done with this, it's now time to actually create shaders. On the stack we call GL create shader twice. Once with GL vertex shader and once with GL fragment shader. And we store them each in the vertex shader ID and the fragment shader ID. Now we have those two shaders. These are just IDs, so handles to find them. And yeah, this is where we have to create our shaders, which is Poggies, because we are going to create a new folder here to the left, call that assets. And then inside assets, we create a new folder, shaders. And then inside the shaders folder, we're going to create a new file, which is quad.vert. And let's create a new file immediately, quad.frag. And let's begin with the vertex shader. That is a version 430. This is the one we loaded in the platform layer, core. And then we do a void main function. And inside the main function, we need to write to a variable called gl_position. And in order to do that, and this is something that I took over from Vulkan, I don't like to use vertex attributes, which basically means I don't like to supply a buffer of vertices to the shader. I like to define them inside the shader because I know that we are only going to be creating quads for now. So that means I create a vector2 vertex array inside the shader that covers all of the corners of a quad. Top left, top right, and bottom right. And then in order to understand what these coordinates mean or how to position them, the Vulkan tutorial has a very nice picture comparing the frame buffer coordinates to the normalized device coordinates. Basically on the GPU, if this is your window to the left, while the middle point is 960 and 540, on the GPU the middle point is 0 and 0. Which means to the left it is normalized. You go -1 to the left and then 1 to the right. And if you go up, you go -1 up and 1 down. But this is for Vulkan. In OpenGL, the Y coordinate is flipped, which means on the top, Y is positive and on the bottom, Y is negative. Which means, if we go back to our program, this is what it looks like. We have -1 to the left and 1 on the Y. And then on the right, we have 1 on the left and 1 on the right. And then we have -1 on the left and -1 on the Y. And then again, 1 here and -1 here. And so this should help you determine where to place these vertices if you want to place them inside the normalized device coordinates without doing any conversion. The conversion actually will happen when we implement the camera. So what we are going to place now is percentage-wise coordinates. And so let's say we want to create a quad that is half the size of the screen. We put everything to 0.5, which means the resulting vertices look something like this. Top left is -0.5 and 0.5. Bottom left is -0.5 and -0.5. Top right is 0.5 and 0.5. And then top right again, bottom left again, and then bottom right is 0.5 and -0.5. If you need a while, take a look at these numbers, but they should all line up quite nicely. And these are the vertices. And obviously what we're going to do here with the GL position, after that we want to index into the vertices and assign the GL position. To do that, we use a predefined variable called GL vertex ID. This vertex ID corresponds to a draw call. So basically what that means is if you call GL draw with 6 vertices, it is going to invoke this shader 6 times. Each with a different ID, indexing into the vertices. And then after that, we supply the near and far plane, the z-axis. For us, it's going to be 1. And then a perspective divide, which I already told you is 1. You can use this and supply a different value here and test out what it does. It should make the quad smaller and bigger because it's perspective. If we are dividing it by 1, we are leaving it as the original value. Okay, that is the vertex shader. Now we switch over to the fragment shader, and this one's quite simple. Of course, at the very top, we have to supply the version core. The only difference here is that we have to actually supply an out location, and we call that the fragment color, which is basically the final color that we write to our image. And then in the main function, we just supply the fragment color to be white. Alright, since these are the two shaders now, we can go back into our OpenGL renderer and load them. This is where we create a character pointer vertex shader, and then we read in assets/shaders/quad.vert. It takes in the file size, which is an int file size, set that to 0. And then we need a buffer or a transient storage, which we will supply our transient storage. And then we do the same thing for the fragment shader. Frag shader reads in the quad.frag. And then if you want to, you can do if checks here if we don't have the vertex shader or we don't have the fragment shader. This assertion will then also block the code at this point, and we can make sure that we catch the error before anything bad happens. After loading in the files, we can connect the sources to the shader IDs by calling GL shader source. They take in the shader ID as the first parameter, then the number of shader sources, and then after that a pointer to the array of shader sources. The last parameter can be 0. This is basically the length corresponding to the shader sources. If not supplied, OpenGL will look for the null terminator in the shader sources to determine the end. And we do the same thing for the fragment shader. And then after that we just call GL compile shader, which compiles the text files into actual code. Testing if the shader compiled successfully is crucial in my opinion, and this is why I want to put the step in here. In order to do that, you have to create an int variable called success. You also have to supply a buffer for the potential error message, and then you can call GL get shader IV. This takes in the shader ID, then the actual enum of OpenGL what you want to check, which is the compiled status, and then a pointer to the success variable. If we don't have success, then we actually want to get the shader info log based on the shader ID as the first parameter, the length of the buffer that we have for the message, and then the actual shader log message. And what I do here is I throw an assertion that basically holds the program at this point and will then log a message to the console with the proper error message from the shader. And of course I do that both for the fragment and the vertex shader. Okay, so now that we have our shaders, we can finally create our program, GL create program. And that returns us an int, and this is where the GL context is gonna come into play. The program ID is the GL create program. Then after that we GL attach shaders, taking in the GL context dot program ID and then the shader ID, which is the vertex shader ID, and obviously we attach the fragment shader as well. And then after that we call GL link program, which takes in the GL context dot program ID. Now after this is done, we should be able to delete the shaders because they are now part of the program, and if we don't need them anymore, we should clean them up. So this is where we can call GL detach shader, taking in the GL context dot program ID and then the shader, which would be the vertex shader ID. We detach the fragment shader as well, and then we do GL delete shader and then takes in the vertex shader ID, and we do the same thing for the fragment shader. Now, I already told before that we are not going to use vertex arrays because I don't like using them, because in Vulkan you don't have to. In OpenGL you have to at least create a GL uint VAO, and then we need to GL generate vertex array, 1 at least, and then supply the pointer to the VAO. And then after that we do GL bind vertex array, which takes in the VAO. And unfortunately we have to do this. This has to be done. If anyone knows why that is, even if I don't use vertex arrays, feel free to tell me, because I've tested this without the VAO bound and it wouldn't show up anything. Even if I am just using a draw call, we generate the vertices in the shader and then we supply the position through the vertex ID. It doesn't seem to work. I don't know why. We need this. Why don't you like VAOs? Well, because I can do everything through arrays. Why would I create a VAO? I can just create a structure and then have an array of structures. So basically I can generate a transform which has a position, a size, an atlas offset and a sprite size and maybe some options and then a layer. And this is included in the shader, by the way. This is inside the shader as well as inside the game. So I can access this transform in the game and I can access this in the shader, or basically I have access to the structure of this. And then in the shader, in the vertex shader, I could just have an array of transforms. And so I'm just accessing the transform's position and the atlas coordinates here. Yeah, and then I supply the position. There is no need to have vertex attributes at this point. The cool thing is I can just change the transform and it will propagate the changes not only to the shaders but also to the game. In my opinion, that is so much easier to work with, and unless there's like a performance penalty, I'm just gonna keep on using it. And so far I've not encountered any performance penalties. This is for later. We can already enable dev testing. We GL enable and it's called GL dev test. And then we call GL dev function, which is GL greater. This is for when we actually have textures and draw more sprites on top of each other. This will help. Okay, and this is our initialization function for now. We're going to add stuff to it later. But now we can create a new function called void GL render. And we don't actually have to do much in this function. we just need to call GL clear color. And this is where it asks us to supply a red, green, blue, and alpha component. This one right here, we have 119, 33, and 11. So using those values, this is going to be our clear color. And then we also want to GL clear depth to a value of 0. And then after that, we call GL clear, which takes in a bit mask. And I don't know why it's called like this, but it's called GL color buffer bit. And then a GL depth buffer bit. Basically, what we are saying is, this is the values that I want to clear with. And then we are actually invoking the clear by saying, okay, we are going to clear depth and we are going to clear color. And then after that, we just call GL draw arrays, GL triangles. The first one is going to be 0 and we want to draw 6. And so if we did everything correctly, this should draw us our triangle, which is, you know, half the size of our screen. But there's one last thing we have to do. OpenGL doesn't know which viewport to render yet. It doesn't know which size to render to yet. And so we need to call another function, which is GL viewport. That takes in a position of 0 and 0, and then a size, a width and a height. And we need to read that from the screen, which we don't have anywhere right now. We are just creating an arbitrary screen size right here, and we are not storing that anywhere. And so this is where I want to introduce our first or another new file that is going to hold everything about input. And for me, input is also considered, since it's tied to the window, the screen size is also part of it. So I'm going to create a new file called that input.h. At the top of the input file, we pragma once, of course, then we include our schnitzel-lib to get access to everything we need. Below that, we create a section input structs, and then below that, we create our input struct, which for now only holds the screen size in X and Y. And below even that, we create the input globals, which will just be a static variable of input. Alright, and then in the main.cpp, I'm just going to quickly hack this in. Input should be at the very top, like somewhere here, include input.h. And then once we create the window, we also write to input.screen size x, which is 1200, and screen size y is 720. Now we have access to this, and the renderer also has access to input, which means in our rendering function, we can use the screen size. Now, obviously, when we change that, we need to make sure that this is updated. But for now, we can do input.screen size x and input.screen size y. Now that we are done with this, we call GL init here. Then we call GL render in the update loop after we update the window. And now I want to quickly make sure by opening the Win32 platform layer that we also handle resizing the window. So case WM size, we need to update the size of the input or the window size so that OpenGL knows exactly what to draw to, otherwise it's confused. In order to do that, we create a rectangle here on the stack, and then we call get client rect, which takes in the window and a pointer to our rectangle. And then we could do input screen size x is rect.right minus rect.left, and the screen size y is rect.bottom minus top. Okay, and that means our input structure is always updated with the correct screen size, and then we know in OpenGL where to draw to. 5 warnings. fopen is deprecated, function variable unsafe, deprecated declarations. Okay, that's another error that we need to add to Clang. So copy this and go over into the build file and add that here. No deprecated declarations. So it looks like we are doing it correctly because we are not getting any errors, but the window is white. And the reason for that is we need to call a platform specific function that is called swap buffers. We need to make sure that we are swapping the buffers on the window, and that is usually a Windows or Linux specific function. Unfortunately, there's no cross-platform function for that. And so we need to call, after we are rendering, we need to call platform swap underscore buffers. And this is a platform function that we have to put into the platform.h file. So open that and then put this here. This is a void function that every single platform has to implement. And so on Windows, if we go to win32.cpp, on Windows it is just called, and let me center this a bit for you, swap buffers. That takes in an HDC, and that means we now need to make that public, because right now and this is the one we created last time, this HDC that we get from the window, we have put that inside of the create window function. Now it needs to be globally accessible from other functions outside. And so yes, we're going to create this as a global variable on top. So static HDC DC. And then we should be able to access this right here. Okay, now that we have swap buffers, we can build the program again. And then let's see if it actually shows up. Good. I mean, we have a background, which is very good. So that means, can we resize the screen? We can. actually. That's a very good first try. Obviously, the triangle doesn't show up, which is kind of sad. I actually like that it doesn't show up, because that means I can introduce you to an application called RenderDoc. This lets us inspect graphics applications, like games, for example, and then we can use these to determine what's going on, if we are actually drawing something or not. So we're going to set the path to the executable that we want to test, and then we are launching the program. Then it shows us, okay, well, it's running on 60 FPS, however many frames it shows, and it's capturing OpenGL. Then we can press F12 to print the screen, and then we can inspect this screen. So we are actually drawing something, that's nice. In the texture, we have no textures. And then in the mesh viewer, it looks like errors detected with draw call. No vertex shader bounded draw. Oh, it looks like I forgot to call GL use program. GL context dot program ID. Now, and obviously I put this there just to show you RenderDoc. It's not like I actually made the mistake. I knew that I didn't use the program, right? We use just to show you that. Stop calling me a liar, okay? I need to sell this. Now it should show us the triangle, of course, right? We shouldn't get any errors, and it shows us the triangle. Very nice. We got a quad on the screen, so everything worked out as planned. Okay, now if we resize our window, the quad is stretching together with the window because we are using the normalized device coordinates from -1 to 1. And yeah, that's how you can draw a quad to the screen in OpenGL while doing everything yourself. It does take a lot of work to set up, but now we have the possibility to change our shaders. Like, for example, we can make this quad red. For that, we only have to switch into the fragment shader, and then we supply the components of each individual color part. Then we build again. We start, and we should be seeing a red quad. Very nice. And this is all I want to show you this time. I know this was a lot. We changed many files. You can see that on the left right here. And some of them are yellow. You know, they're complaining a little bit. A bunch of warnings here. We're going to fix the warnings next time. I'm going to push this. And the next time, we're going to actually add in textures. So, and then create a rendering interface in which we call draw sprite or draw quad. So we can basically position the sprites properly. And after that, we're going to make a 2D camera, an orthographic camera, so we don't have to worry about scaling and positioning pixel art properly. We can just work within our game world and have a very nice, it's very easy for us to use it. Until then, if you liked the video, please make sure to like and subscribe for more, and see you in the next one. Have a good one. Peace! Oh, excuse me. Sorry. Excuse me. I'm sorry, guys. Excuse me.